Laura Podolsky with the National Center for Sustainable Transportation. We're delighted you joined us for today's webinar, Monitoring Sea Level Rise at the Local and Regional Scale. This webinar is brought to you by the National Center for Sustainable Transportation in partnership with the Institute of Transportation Studies and the Road Ecology Center here at the University of California, Davis. Before we begin, I would like to provide a quick introduction to the National Center for Sustainable Transportation. The center is one of 5 national centers designated by U.S. Department of Transportation as part of their University Transportation Centers program. Our mission is to advance a more sustainable transportation system through cutting-edge research, direct policy engagement, and education of our future leaders. Our consortium is led by the Institute of Transportation Studies at the University of California, Davis, in partnership with the University of California, Riverside, University of Southern California, California State University, Long Beach, University of Vermont, and Georgia Institute of Technology. Today's webinar features new research from the National Center for Sustainable Transportation led by today's speaker, Fraser Schilling. For our time today, we will start with a presentation from Fraser Schilling, followed by comments and reflections from our special guest respondent, Mark Reese. We have reserved plenty of time for questions from the audience. If you would like to submit a question for our speaker or guest respondent, then please type your question into the chat box located in the lower left hand of your screen. Everyone will be on mute for the remainder of this webinar. You can also use this chat box to let us know if you are running into any technical issues, and we will do our best to help you. We will address all questions at the end of Fraser's presentation, so if you do have a question for a specific slide, then please note that slide number when you submit your question. We will be recording today's webinar and posting it on our event page for later viewing. A link to that webinar recording, today's presentation slides, and the associated report and policy brief will be sent to everyone in a follow-up email that will be going out tomorrow. So without further ado, I'm very pleased to introduce our speaker and distinguished special guest respondent. Dr. Fraser Schilling teaches in the Department of Environmental Science and Policy at the University of California, Davis, in addition to serving as the co-director of the Road Ecology Center. Dr. Schilling has 3 main areas of research: environmental pollution and policy, transportation and landscape ecology, and sustainability indicator systems for whole system condition reporting. Dr. Mark Reese will serve as our special guest respondent today. He is the Director of Marine Extension and Georgia Sea Grant and Georgia Power Professor of Water Policy at the University of Georgia. His expertise is in non-point source pollution management, water resources, stormwater management, coastal erosion processes, and sustainable and resilient development. At the University of Georgia, Mark has received a recognition as a fellow in the International Soil and Water Conservation Society and is a Walter Bernard Hill Fellow, the university's highest honor for public service and outreach. So with that, I will turn it over to Fraser to start his presentation.
All right, thanks very much. I'm going to flip back to the title slide here. This is a collaborative study. So the other people listed on the title slide here are really critical for making all of this work. David Waitchen at the Road Ecology Center, Eric Gohalva, Christine Sir, Ted Grosholtz in my department, Environmental Science and Policy, and then Kimberly Andrews at the University of Georgia, and then Allison Ballard, who is an undergraduate who helps a lot with the study in Georgia as well. I also want to acknowledge that this work was made possible because a lot of people in the Bay Area, and in the San Francisco Bay Area, and in Georgia gave us land access, permits, really facilitated the system that I'm going to talk about. Also, the work was initially funded by the National Center for Sustainable Transportation, supported by US DOT through our University Transportation Centers program. So I'm going to talk about sea level rise, and most people are, I assume, are familiar with the concept. Probably a lot of you are familiar with the projected rates of sea level rise. And so the top graph is from a recent, becoming less recent NOAA report, I think back in February, which was looking at different sea level rise scenarios, both globally and then regionally around the United States. And they added a new curve which is really important here, and that's the red curve on the top chart. And then there's corresponding values in the table at the bottom. And this is the extreme low likelihood trajectory for sea level rise around the globe, and then it's expressed differently in different regions. And I boxed one area of it, and this is 2020, 2030. So in the next couple of decades, which is within our community planning horizons, our transportation planning horizons, and a lot of us will still be around, thankfully. And so this is really in our experiences is in this box. And if we look at the red curve, which is the trajectory we're on generally for climate change, is the highest slope for everything. And if you look at the table at the bottom, it shows you the change in sea level with sort of a bathtub model kind of approach. For 2020, 10 centimeters, and for 2030, 24 centimeters. And this is relative to the year 2000. So that's 4 to 10 inches. And for a lot of coastal areas, and especially the ones I'm going to talk about, that's a lot of sea level rise in terms of changing the baseline, especially when you consider that you have coastal rivers that may change in their flood stage, and also we have phenomena such as El Nino, which may change the annual actual sea levels at coastlines, especially in the winter. So, and then hurricanes down the East Coast, and Georgia is starting to experience more of those. So this is sort of a changing baseline and a new normal that we have to adjust to. The physical processes that will come into play, I'm mostly going to talk about tidal marsh systems on both the California and Georgia coastlines. And this diagram is just a simple one showing the different stages of marsh from the fully inundated subtidal up to the uplands where you'd expect to have a different vegetation type. So in the intermediate area, you have low marsh plain or mid to high marsh, and transition to upland. As we change the sea levels and the average sea levels and also the periodic storm event sea levels, we change the dynamics on that marsh surface, which is very important both for marsh protection and restoration, but it's also important because those areas are protective of a lot of shoreline infrastructure we take for granted. I also added on here, thanks to Mark Reese for this one, groundwater intrusion, which is certainly important in places like Florida with very porous geological substrate, but it's also important in other areas with even clay and silty soils, such as the San Francisco Bay Area and other parts of the East Coast, where we're starting to see saltwater show up well inland, suggesting that our land loss, functional land loss, and even material land loss is going to be both affected by surface processes with wave action and higher sea levels, but also subterranean processes, which we probably don't understand quite as well as we should. And so storm events have been really critical recently, especially in Georgia, where they've had 2 hurricanes in the last year, which is, I think, quite a bit more frequent than they're used to, where maybe it's 1 per decade. And I want to show you an example of an area on Jekyll Island on the coast of Georgia. And this is looking at the line of trees masks a highway that goes out to the barrier island, which is Jekyll Island. And this is common along the East Coast, where you have a barrier island connected to the mainland via a causeway. In this case, the causeway sits on a berm on top of the marsh plain. And I'll show you, this is one high tide, and the next high tide is theoretically a lower high tide picture, but it's during the hurricane, and you can see that the elevation of the water is coming right up, I'll tell you, it's coming up to the causeway, and in this case, it went over the causeway, and that was true for another island causeway as well. And so as we change the base elevation across these marshes, we potentially change the marsh and its protective function of the shoreline infrastructure, and we also are going to eventually flood these causeways and make them non-functional. And so storm events are really important to keep track of, not just the gradual change in sea elevation. So what's the problem? And this is the problem that I address in this talk and in the study that we're engaged in. And that is that coastal infrastructure, whether it's roadways or residential areas or industrial areas, and shoreline ecosystems are immediately adjacent to each other, and they strongly interact. Usually we think of it as a negative interaction from the point of view of the marsh, where the developed landscape is negatively affecting the marsh. But there's also situations probably where the natural system is negatively affecting the infrastructure. And certainly the natural ecosystem here, the tidal marsh, is protecting the inland communities and infrastructure from wave action, tidal action, and inundation. The problem is that these marshes can't migrate inland, and so as they become increasingly affected by sea level rise and storm events, they will degrade and eventually go away, and then we've lost that very important service along our shorelines. To put it in perspective, there are about 4 million acres of coastal salt marsh in the lower 48, providing different kinds of services. The guidance for how to think about and plan for sea level rise in shoreline planning, both community planning and transportation, Federal Highways Administration and Caltrans suggest the use of predictive models to plan for protection of shoreline infrastructure. They both also suggest we should monitor impacts on the shoreline, but there's no guidance provided for how to do this, and that's really the focus of what I'm going to talk about. One of the issues is that our predictive models are not quite up to the task currently. That doesn't mean that they aren't going to be soon, or that some models out there that haven't been published yet are doing the job. But I'll give you an example right here. The top left image is from a model that I commissioned for a study along Highway 37 in the San Pablo Bay. The green areas are protected by berms and levees, or they're high enough to not be inundated with a 12-inch sea level rise. And so I circled the area in red because that's a very important area there, where if it floods a coastal highway and also an important county road and cuts off the function of those roadways. So under 12 inches of sea level rise, our model said that this area would not flood. But a different model conducted by climatecentral.org suggested that that area would flood, which is the picture at the bottom with the red circle. So same data sources, the LIDAR data, probably similar modeling approaches, and we look like we're on the cusp of that area flooding, but we don't know for sure. With our modeling with 24 inches of sea level rise, that area does flood, and that's the diagram on the top right. In this last winter, we had about 10 to 12 inches of excess sea elevation beyond what is normal or predicted, and that area came very close to flooding but did not actually flood. So why should we track change along the shoreline in response to sea level rise? And there's several important issues here. The words here really don't convey the magnitude of the problem really well. For example, the replacement cost of infrastructure exposed along the U.S. shoreline with just a meter of sea level rise probably will be in the trillions. Economic activity along the coastline is highly dependent upon exposed infrastructure, including communities where people live. And then we're going to have loss and or change of shoreline ecosystems, tidal marsh, beach systems, et cetera, anything along the coastline that's affected by sea elevation and storms. And then there's a reinforcing effect between the infrastructure and the ecosystems that are immediately adjacent. So much of our development is on the coastline that we often have this kind of interaction between infrastructures and ecosystems. And so how do we track change? And that's the focus of what I'm going to talk about across different scales. A lot of our data collection globally is at a decadal scale or annual scale using satellites and remote sensing. Typically the publicly available data has about 30-meter resolution. When we get down to lower elevation photogrammetry and LIDAR, we have a much finer temporal scale and spatial scale on the order of months to years and meters squared, and even down to tens of centimeters squared. And then Very fine scale, and this is more and more becoming more and more important, and the technologies are being developed. We have hour or monthly time frames and centimeter resolution, and I'll talk about some of that in this talk. Okay, so I'll talk about this first one, and this is some recent findings, a study that's ongoing right now using both satellite photographic imagery and also remote sensed imagery for multispectral analysis of plant growth. And so this is just showing a couple of, I'm going to show you two different areas in the Bay Area. This is near a town called, or an area called Corte Madera. The white areas in this image indicate the position of the shoreline in 1987, and then the underlying photograph is from 2015. And so if you compare the white, I wonder if I have a, is that visible over there? Yeah, it is. Okay. So the white line that's coming down here underneath the yellow arrows, that's the coastline in 1987. By 2015, the shoreline was following this blue line, and it basically retreated along parts of the coast just in 30 years. In another area down here, we had channels starting to form in the tidal marsh which were not present previously. And so we have a change in the geomorphology of the marsh plain. In another area, this is in alongside Highway 37 in the North San Pablo Bay. I think I've lost my, oh, there it is. The highway runs, maybe I can get a pointer. There we go. Okay, so the highway runs alongside this natural marsh is in this area alongside the highway, and then there's some restored marshes inland or inboard of that. This white area is all water, and the white shading here is from 2002, and it's showing the shoreline in 2002, highlighted here in green, and then the underlying photograph shows the shoreline in 2014, and you can see that it's moved quite a few meters inland. Another really important thing, and this is something you can, if you're in California, if you're in the Bay Area, you can see for yourself, is this area here changed from a marsh plain with these green circled areas here were basically pools of water that were becoming mudflat in 2002. By 2014, the mudflat area had extended, or the devegetated area had extended to cover almost half of this marsh plain area. And over the last winter, the vast majority of this area here was inundated for months, and this devegetated area is expanding. So we've got a change in both the position of the shoreline and also the composition of the marsh plain. So getting it to a lower elevation, so that was looking at satellite imagery. If we start using LIDAR to understand surfaces, most of our data comes from aircraft-collected LIDAR, and so that's using aircraft to carry the sensor at relatively low altitudes, and so you get high-resolution surface maps or terrain maps of the Earth. And so our data from most of the U.S. coastline was from 2010 and is curated by the U.S. Geological Survey, and I think it was funded by NOAA. But we're moving increasingly to unmanned aerial systems or unpersoned aerial systems as a way to support the LIDAR, which will mean we can get even lower elevation. And I want to show you an example of how this could be useful. This is looking at elevation change in a shoreline marsh in the San Francisco Bay. This is in 2004, so this is LIDAR flown in 2004, where the blue area is inundated. The green area here is shoreline. The white here, these are buildings, these are residences. And this area here is a tidal marsh, and you can see the stippling and the green are elevated parts of the marsh. By 2010, in 6 years using LIDAR, we see that the green areas are mostly gone, meaning that the marsh elevation has changed in this very fine scale picture. Okay, so the finest scale that we've got to so far is using fixed position time-lapse cameras, and this has been going on over the last 3 years in the Bay Area, where cameras are positioned to look at different parts of the coastline to track, and this is also, in California and Georgia, to track fine-scale changes along the shoreline, ostensibly due to sea level rise, but it could be due to other causes as well, and that's something that we'll control for. So in the North Bay, this is the North San Pablo Bay, and the Central Bay, so the San Francisco Bay Area, we have about 20 stations, and then we have another 12 on Jekyll Island. This is the tidal marshes and causeway leading out to Jekyll Island, which is this sandy spit and some upland area island out here, and the Atlantic Ocean is on this side. So each star represents a location of a time-lapse camera. In Georgia, these have been going for almost 2 years, and in California for 3 years for some locations, but most locations about 2 years. The method is that we take a commonly available trail camera. Obviously, you can make these very high resolution. We use either 8 megapixel or 14 megapixel settings on these cameras. They're fixed to posts. In this picture, you can see a post in a custom location if there's no other structure, or if there are structures available, then a structure is used. This is a very challenging part of this because the shoreline is very dynamic, and just finding places to position the monitoring device is itself a task. The cameras are set to take images every 5 to 15 minutes, but most of them are set at 10 minutes. And this is so we have a sort of a practical amount of data, or it might be impractical by now, but it allows us to catch the peak low tide and high tide. We began collecting images in 2014 for some sites in the Bay Area, and this project was funded by NCST in 2015 to 16. And basically, we take, there's several ways you can use these image data. I'm just going to show you one. And basically, we capture the area on the land surface. In this case, the land surface is tidal marsh and is periodically inundated. And so this trapezoid here represents what would be a rectangle on the ground if you were looking from above. And so obviously, looking from above, this shape would look different. And so we want to capture an area on the ground. And so each image is rectified to correct for this distortion, this distance distortion. Are we having trouble with?
Yeah, I want to check in really quick. Can everyone see the slide titled Quantify Inundated Area? That's the title?
You can see it?
Okay.
So it might be just your computer?
Okay. Sorry for that interruption. Just wanted to make sure.
Okay. So we rectify each image so that we're capturing basically a rectangular area on the ground. And then we process each image so that it has high contrast. And you can see this on the right, where white equals a wetted area and black indicates or represents a non-wetted area. So, and it comes from the fact that when you take a picture at an angle like this, as you can see in this image, and there's water, then you have a lot of light reflection, and so you can do this kind of conversion. It is not 100% accurate because you do get some shading by vegetation, and so that's something that we're working on as well. So the inundated area can be quantified as % of the total rectangle, or it could be turned into area if you know how many pixels there are per square meter, for example. So to look at how sea level rise might be monitored using this approach, I took a single tidal cycle, or this is showing a single tidal cycle. I took multiple tidal cycles. The tidal elevation from a tidal gauge is shown in the solid line for one mid-tide to low tide part of the cycle. And then the dots represent the white area or inundated area in each image that was taken every 10 minutes. And so you can see that there's a slight lag time between the peak inundation indicated by the highest dots on the graph and the tidal gauge indication of high tide. So we've got about a 2-hour lag time while the marsh fills up. And so one interesting question was, how sensitive is this method to a very small change in tidal elevation? And across multiple tidal cycles and across 2 different stations, we were able to detect differences for only 1 centimeter of sea elevation change, or really less than 1 centimeter sea elevation change. This suggests that we could potentially use this method to look at interannual changes in inundation at certain monitoring sites. And so if we have enough of these spread around the coastline, we can start to measure sea level rise in almost real time, or the change in the shoreline due to sea level rise in almost real time. So this is just looking at inundation. You can also use this same approach to look at the dry area at low tide and see if that changes, or the wet and dry area at low tide, to see if that changes with sea level rise too. Because you would expect that as sea level rises, your low tides would get higher and higher. So storm events are really critical because they may be the source of a lot of change on the shoreline. Certainly seems like it's heading that way. And so I wanted to show you an area on the San Pablo Bay shoreline looking at a marsh plain. This is at a fairly low high tide, this first image. And then about a month later, there's a slightly higher high tide, and you can start to see some water in the distance. And then we started to have a series of storms. This is over the last winter, and those of you in California will remember that these were the storms that closed Highway 37 in this area and led to a lot of other problems on the coastline. So here we start to have a lot more intrusion. This is not a very high tide. It's not a king tide in terms of predicted height, 6.4 feet. The actual elevation was 7 feet, so it's more like a king tide in its actual elevation. The next day, the high tide was not predicted to be much higher, but the actual sea elevation due to storm action primarily was 7.9 feet. And now we've gone from the marsh plain being largely just partially flooded to almost completely flooded, and this is all the way up to the edge of the roadway, Highway 37. And then 2 days later, the sea elevation had only changed by about 1.5 inches, but we had completely changed the inundation level of this marsh plain, and now the marsh plain is tidally connected to the bay. So there's a continuous flow of water back and forth as if the marsh plain was now part of the subtidal or mudflat. This effect gradually receded, and actually by the summer, in most of these areas that had been fairly severely flooded, most of the flooding had gone. But it still took months for this situation to change, and has led to a fair amount of devegetation in these marsh plains. So in conclusion, really I'm describing and advocating for methods like these as the only way that we're going to really track sea level rise impacts in real time, and really the best way to validate predictive models, because predictive models for these areas should tell us how changes are going to occur, and we can collect these data fairly rapidly to find out if indeed we're on a particular trajectory indicated by a predictive model. Our next steps, the time-lapse cameras are still out there, still collecting data, not funded at all currently for about the last 1.5 years, but it's a really worthwhile thing to do. There's additional information we can collect with time-lapse cameras, which is quite important. For example, bird counts, for those interested in maintaining that function, and also vegetative cover change. We just received funding for a UAS-based LiDAR, so we'll be starting that up in the Bay Area and along the open coast in collaboration with Shoreline partners, both from a permitting and also from a data exchange point of view. And then in Georgia, hopefully with the help of Sea Grant, we'll also be carrying out similar kinds of studies. And we'll be looking at vegetation change and geomorphological changes along the shoreline. And then finally, with satellite and remote sensing, this is in collaboration with a couple of students here at UC Davis. We're looking at changes in the rate of shoreline change in California and Georgia to see if it's even measurable, and both the rate of change and the location of changes to see if we can identify places where changes are identifiable over the last 30 years of remote sensing data collection. If you want more information, please feel free to ask questions now or email me. You can also check out our website. A couple of different websites are shown here, or follow us on Twitter. Thank you.
Thank you so much, Fraser. And we are going to open the phone line for Mark Reese to provide some opening comments and reflections. And then after that, we will open it up for questions. I know that some folks on the line have entered them in the chat box, and so we flag those, and we will get to those questions. And again, I noticed some people have raised their hand. If you can chat with us via the chat box and let us know if you have a question, or for our speakers, or if you're running into technical difficulty, then we can help you. All right, do we have Mark unmuted? All right, Mark.
Can you hear me?
Yep, we can hear you.
All right. Well, thank you, Fraser. I enjoyed hearing that presentation. And for the rest of you, I met Fraser a few years ago when he started setting these cameras up on Jekyll Island. And I got to admit, at first I was like, well, what are we going to be able to do with this information? But it's amazed me how much utility there is in catching data like this. We have a lot of efforts going on with resiliency and helping communities respond to nuisance flooding and sea level rising. And one of the things that I think we learned real quick is that using bathtub averages and an average increase of a few millimeters doesn't sound like a lot, but when we put that on top of extreme events, storms or king tides, they can cause a lot of impact. So sometimes people get lost in the smallness of these numbers, but the impacts are quite large, and trying to figure out how much is acceptable is often a difficult question. If it's your home that's getting flooded, it's definitely unacceptable. And I think some of these tools can help play into answering some of those questions, as well as what are the impacts besides the flooding. I mean, I'm anxiously awaiting Fraser's analysis of some of the cameras that survived Irma, so that we can begin analyzing all the images taken during what was one of the most extreme events we've seen along Georgia's coast, and how did the infrastructure respond. I mean, we have cases where we've got seawalls and revetments that have failed, and we've got camera footage that was collected of those failures. And to me, it's going to be interesting once we can go in and analyze, how exactly those failures happened, or what caused them beyond, just the flooding. I'm also interested, causeways, and Fraser had several pictures of the Jekyll Causeway. Tybee Island on the northern end of our 100 miles of coast is only accessible by one causeway, and it floods routinely. I mean, we have 12 to 15 times a year on our extreme tides where the road gets closed, and I would love to have some cameras out on that road, because we need to be capturing what are the impacts on that road itself, beyond just having to close the road and all the impacts associated with that. Is that weakening the road system and network, and are we setting ourselves up for greater failure? Some of the other things I really wanted to share is, Fraser talked all about how this is great for monitoring infrastructure, and I know that's the focus, but it's been amazing to me seeing what else we can do with these images. We've got folks that are looking at some of these images and trying to monitor things like wildlife. I mean, you can actually pick out in these pictures, different types of birds or other animals using the marsh or the roadside. and watch for changes in, by season or over time, and in the number of populations you catch in these images. And I think that that's going to be some really interesting uses for this information, as well as recreational users. And you're capturing everything that's going on out there in these images, and so we can analyze these images for a lot more than just what the water level was, which is the focus of what Fraser's doing right now. But I think when we begin collecting these data sets, we're going to find that there's much more utility to them. One method that Fraser mentioned a little bit that we're using in Georgia is using UAVs to take pictures from a variety of angles, and using a software package called Structure for Motion to recreate, to make DEMs of some of our shorelines. And I have a graduate student using that in a project where she's analyzing the differences in erosion rates between living shorelines and bulkheads or seawalls. And at first we were wondering, well, can we capture this data by just doing a flight over it and taking pictures? And I think her work is showing us that yeah, we can get enough accuracy where we can see changes in shoreline erosion over time. We have flights from pre-Irma and post-Irma, and we can begin looking at what are the impacts of that storm on the shoreline. And that's really, to me that's fascinating, because historically we wouldn't have been able to do that because of cost. To get a ground-based LiDAR, or to have somebody make a flight for you with LiDAR, was just made the research too expensive for us to do. But now that we can just send up a UAV and see these differences, we can monitor a lot more and capture some of these single event occurrences. And so that leads me to, I think, the question I'm going to give to Fraser for him to share with y'all, and then we'll move into questions and answers. Is you didn't really mention much about the cost of some of these methods, and I'm sure that's the focus of some of your research, but can you talk a little bit about the cost of the various methods you're proposing, and what that would be for somebody?
Sure. Thanks, Mark. And I can start with that as the first question. We have quite a lot of questions now in the chat box area. The camera system, time-lapse camera system, with 36 cameras, the startup costs and then maintenance for a year was about $60,000. And the cost since then is a bit unknown, since it's all free labor and volunteered batteries. But I suspect that the maintenance cost isn't a lot lower, because there's also an analytical component to that. So for that size array in those two areas, it's about $60,000 direct cost. There's obviously overhead for different institutions. For the LiDAR, that's changing rapidly. When I first looked at LiDAR in 2014, 2015, I got comments back on a proposal suggesting UAS LiDAR, and it was hard to get pucks back then, pucks being like a hockey puck-sized LiDAR sensor. And now it's a lot easier, cheaper. The startup, for those of you who track DIY startups, the startup for one LiDAR puck was $300 on a Kickstarter campaign. It's now commercially available for $6,000, so we can kick ourselves collectively. But there's a lot of models out there coming down. The UASs, if you mixed in some cameras, the whole package could be under $10,000 as the LiDAR puck cost comes down. So we have one of those systems that will start up in January, and combined with other sources of data and definitely some good elevation correction or monitoring with RTK GPS, that means we can look at several kilometers of shoreline at about the same cost, about $50,000 a year. So I think that at the scale of Jekyll Island, the San Pablo Bay, with using these combined systems for about $100,000 a year, maybe $200,000 a year, if we throw in some better data analysis, that's about our monitoring cost. I think it's a really critical question because it brings up having a coastal monitoring system like this, which is really what we're shooting for. And how do we have a shoreline monitoring system that's similar to our ocean monitoring system, so that it can track these changes? And it's especially critical given the amount of investment we've made into shoreline protection, both socially in terms of statute and financially in terms of restoration, but also the amount of economic activity and property at risk means that this is a really critical exercise. So thank you, Mark. Hope that helped. And
great. Yeah, we have quite a few questions, so let's get to it. There was quite a few that were on slide 16.
Okay.
So if you'd want to toggle there, excuse us as we toggle back to that slide. There's a couple questions on how the shoreline was delineated, and does it use the same technique? Yeah. So this is an illustration, but basically I used a similar kind of contrast approach. This was a bit of a thumbnail at first, and then I went through 15 or 20 different locations to see if things were actually still measurable. And so by setting the contrast in the image, you can find, quote unquote, the shoreline. Now, there's a better tool out there. I think USGS might have it, where you can automatically detect the shoreline. I think it's worth really drilling down and testing that in these systems so that because you know that you're not catching a different tidal situation in different images. So this was some of these images were cherry-picked for high resolution, so there's no cloudiness, and you can clearly see the shoreline. The image underlying in this slide is from 2014, and so you can see the shoreline there, which is a nice berm, a natural berm along the shore, and it used to be about 20 meters further out, 10 to 20 meters further out. And so again, for this slide, too, there's questions on how do you account for the changing in the tide, as well as how do you account for were the photos taken in the same season across different years? Yes, same season, different years, and I only used places where you can see a clearly delineated shoreline where there's berm. In other images from each of these years, you would see the mudflat because of the timing of when the image was taken. And so the images were selected to be basically high tide, and so you can see the clear edge of the shoreline at high tide. Okay, great. This question is for the slide, and there's not a number, so we might have to do more toggling about the LIDAR work that you've been doing. So were the marsh LIDAR corrected for vegetation effects? That's a really good question, and it points to one of the critical issues with LIDAR. So I'll just do a little sidebar. Those of you who do predictive modeling or use the predictive models, the 2010 LIDAR for the U.S. shoreline, it has issues with detecting vegetation, and in our models we think of it as the ground surface, but it's actually the vegetative surface. In this case, these are probably a combination of vegetated and ground, and Ted Grossholtz, I think, is hopefully on here. These data are actually from him, my collaborator at UC Davis.
Can you see if he's on there?
I do not see.
So this is a small marsh area that had a lot of active research going on, which is why they even collected LIDAR for it. And my recollection is that it's a combination of Spartina and mudflat. And as conditions changed, the vegetation was lost and the marsh elevation was lower.
Okay, great. And I think this was a slide where you were explaining how, for the time-lapse cameras and catching the imagery. So how did you correct for lens distortion?
So I didn't mention that, but that's part of the, let's see if I can, oh, this is the other direction. That's part of the correction process during the image analysis. Let me go to that. There's actually very little distortion, but it is corrected for with these particular cameras. Most camera manufacturers will share the lens distortion number that you need to do this correction. The software allowed for that distortion to be corrected, and so it was corrected.
Okay, great. And our next question is asking to please expand on how you will do shoreline change analysis from the satellite resources.
So that's just starting up, and we are actually figuring that out. But we are going to use basically NDVI to look at shorelines and then some other data as well. We are hoping to get beyond the 30-meter resolution barrier. It is possible to get higher resolution data, and because we have students involved, I'm hoping that we'll be, and we don't actually have funding for it, hopefully we'll be able to get the high resolution data for free for certain parts of the U.S. coastline. We're going to start with California and Georgia.
Okay, our next question pertains to the Bay Area. It says many groups rely on the 2010 NOAA and USGS LIDAR imagery. Is anyone focused on getting funding for collecting updated regional LIDAR for the Bay?
I don't know the answer, and it's possible that someone else on the webinar knows. And so if you do know, if you could just type that into the chat box, and hopefully we'll get to it. But yeah, I don't know. And I think that at this point, it may be more useful to think about if we collect more LIDAR data, how are we going to collect? How are we going to correct for elevation issues with the LIDAR data? So this is something that was done really nicely by someone at the Vallejo USGS office. I'm blanking on her name. Whose technicians went out and did some RTK GPS measurements on the marsh plain and found that the LIDAR data were overestimating the actual elevation of the ground, which makes sense because it was heavily vegetated. So knowing where the actual ground elevation is, especially for berms and levees, is really critical for any of this modeling.
And our next question, and it looks like Fraser took a sneak at this question because he's already went to the right slide. Oh, okay, so he's just intuitive. So this question is about the cameras that you use. So which Bushnell model did you use, and any problems with theft?
It's a 2015 model, unfortunately named Aggressor, and it's HD. But that has to change over time because we get theft is not an issue with these cameras as much as salt damage. So we're on about a 2-year cycle for camera replacement, and when you do that, you inevitably end up with new models just because the old models are not available anymore. So hopefully that's not an issue as long as you keep track of lens distortion, and usually you're just ending up with higher resolution images.
So this next question also has to do with the camera placement. So how far was the camera from tide station, and does that need to be accounted for?
It's good to know about it because you can actually track the peak in inundation due to high tide using the images themselves. It's not critical to know when the high tide at the tide station was. It's more critical to know how high the high tide was. And in this case, the gauge, the tide gauge is about, from the images I showed, is about 5 kilometers away. in the San Pablo Bay.
Great, and it looks like Kimberly Andrews also shared the story for Georgia that they have not had any stolen in Georgia, only destroyed from chronic exposure to the elements, as Fraser also suggested.
And I should say Kimberly is a critical partner and collaborator in this, and is really is the leader on the barrier islands in sharing these methods, getting these methods developed so that we can track shoreline changes in real time.
Okay, our next question is, you discussed, Fraser, that these monitoring methods can help validate sea level rise models. Do you have any examples of where time-lapse imagery data has been used to do this?
No, we've started to do that here in the San Pablo Bay just because the last winter allowed us to mimic what 12 inches of sea level rise would look like. And so, but I should say that there isn't any funding currently for this, and so it's as we can, we do it as we can. But the last winter was a really great not only wake-up call for what 12 inches of sea level rise could do, but also a great mock-up of, from a data collection point of view, a mock-up what 12 inches of sea level rise looks like in terms of inundation and potential marsh change.
All right, we have another question that's come in. So why is it important to invent a new way to monitor sea level rise when you can do it with vertical high-resolution radar system, which is currently available?
There's different kinds of information that I think you would get with these different methods, and it's complementary, some overlap, non-duplicative in a complete way. Oblique close-up imagery gives you a different kind of view, and it's very, 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 very low effort for what you're getting. So an image every 10 minutes continuously for years is a challenging thing to do. So this is one way to do it, but it has its own limitations, and there's only so much correction or rectification you want to have to deal with. So the complementary imagery from above, LiDAR from above, in terms of UAS, I think is really important. And then obviously the very large area satellite-based approaches are further complementary.
All right, we also got a comment from Eric, and I apologize in advance for how I'm going to pronounce your last name. Oh, okay, so Fraser already knows
project too.
So Gralva, he said they did lose a camera in the SF Bay area, likely due to a placement near a fishing area with high public use. So thanks for that clarification, Eric. So one of my questions, I think that is all the questions that we have that have come into the queue. My computer is frozen up quite at a great time. So if we do have other questions, I'll look to Natalie to flag those for us and share those with us, who's also in the room with us. So one of my questions, I know my familiarity with this project is that you did involve a lot of agencies in the Bay Area, Fraser, and I'm curious if they've shared any feedback with you, had discussions on how they see the data that you're collecting and the tools that you're developing. How do they see that integrating with their practice and planning?
Yeah, so the diplomatic answer is that it's an ongoing discussion, but I think it's certainly further along in Georgia where the agencies are taking these different kinds of information and actively engaging with them. I think what might be happening in California, and I think this might be true in some other states, is that there's been a fair amount of momentum using predictive models, and I think that whether it's the methods that I just talked about or some other method of direct monitoring versus predictive modeling, it's hard to change direction. It's hard to reverse directions and to back out and say, okay, well, maybe the 2010 LiDAR-based predictive models weren't the way to plan for billion-dollar infrastructure changes. And so I think that's, correcting course is going to have to happen, and especially when we're talking about very complicated and expensive areas like the San Francisco Bay Area, let's say Puget Sound, Chesapeake Bay, et cetera. There's a lot tied up in doing this right, and I think that makes it very challenging. In terms of restoration groups, so non-built infrastructure, there's definitely been, they see it as a useful source of information. I think that it's going to be generally true for shoreline ecosystem advocates and people who restore them, that watching them go away is going to be very difficult, and that's essentially what this is about. And so there's a admittedly depressing angle to doing this, measuring the rate of sinking of the Titanic, basically.
So we do have another question. It's about how do these methods, especially it sounds like they're referring to the time-lapse cameras, evolve over time. So eventually the whole frame of the camera will be water. So how, potentially, I don't know, and we're very in the early stages. So how would you respond to, how do you set your cameras so that you can collect data that will be useful over the long term here?
So and that's been really a challenge that's hopefully solvable by webinars like this and further discussions. The owners of the high points on the coastline don't necessarily want cameras on them. So the bridges, the communication towers, but those are really the way that you would be able to solve this, is to so that your frame captures for very long periods the area becoming inundated, and so you don't max out your frame, which is essentially what's happening for some of these, is that it's becoming inundated and then getting taller, higher, and so but you're not measuring that because it's just wetted area. But that's just the high tide. The low tide is really important here too, both from a habitat point of view and also from understanding change. And so we're looking at both ends of the spectrum. And so even if we max out the high tide inundation measurement, we can still track how the things are changing at low tide.
Great. Thank you, Fraser. So this will conclude our webinar today, but before we do sign off, I just want to thank again everyone for joining us today. It was really impressive, the list of participants that we have and the agencies and organizations that all of you represent. I would encourage you, if you have feedback for Fraser, if you're interested in the study, please, Fraser's email is on the screen. We will also be sending out an evaluation survey where we hope that you'll take a moment to fill that out, let us know how we did, and also you share your feedback on this specific research project and what your thoughts are on future directions. I would also ask that you mark your calendars for our next webinar. It will be on January 17th, and that will be on new research from Giovanni Tricella at the Institute of Transportations at the University of California, Davis. I'm looking at the adoption of ride-hailing in California among millennials and Gen Xers and what this means for other travel modes. So are they taking car sharing and Uber and Lyft more, and in doing so walking away from public transportation and driving alone? So thank you again for everyone's participation, and a special thank you to Mark Reese for joining us as our special guest respondent. I hope everyone has a great rest of the day.
Thanks, everybody.